Hello everyone. In this session, I am going to talk about Clarke and path transformation. And they are also known as ABC to alpha beta transformation and alpha beta to DQ transformation. So, in case of induction motor speed control, that is being already discussed in several aspects or in different contexts in several venues. There are different ways to control the speed of the induction motor. That is, either you can control the speed of the induction motor by controlling its stator side or by controlling it at the rotor side. Again, the rotor side control has different techniques, rotor resistance control and slip cover recovery schemes. But to go further, in order to improve the control technique, space vector modulation techniques are generally used. The concept of space vector modulation is already been explained. You can find it in the another video which I have posted here. But in one aspect, in some cases, in order to make or in order to simplify the control scheme, the transformation techniques are applied, and such a transformation is what we are going to discuss. I am going to explain in this video. Alright. So let's move on to the slides. Just have a look at the introduction part. This is simply giving an overview of what is called the transformation and how the transformation matrix looks like, or the transformation equations looks like. The process of replacing one set of variables by another related set of variables is called transformation. So here, as I mentioned before, in the Clarke transformation is nothing but converting this ABC spacer into DQ spacer. Similarly, Clarke transformation is converting ABC frame into alpha beta frame, and path transformation is converting this alpha beta frame into DQ frame. It can be, again, this alpha beta frame can be transformed into ABC frame. That is what we call as inverse Clarke transformation. In the same way, when you are transforming this DQ frame into alpha beta frame, that is what we call as inverse path transformation. Okay, so have a look at this general form of transformation equations. So the new variables, let us say, as I just mentioned now, if you are going to do the transformation from ABC to DQ, then the new variables are DQ. For example, if you are going to convert the ABC into alpha beta frame, then the new variables of alpha and beta, then you will have a transformation matrix, and the old variables, they are A, B and C. And in the same way, the inverse transformation is also done. So the transformation matrix is a matrix containing the coefficients that relates new and old variables. That is what I have just explained with the help of this transformation equation. It will have both the coefficients of both new and old variables. They are relating each other. Okay. This diagram gives a detailed overview. Once you are able to understand this diagram, then things will be a bit more simple to understand. When we talk about this transformation techniques, whether it is Clarke transformation or path transformation, from the outlook, actually it gives a feel that it's quite tough or difficult to understand the concept. But if you are having the fundamental idea about the phase current, phase voltages, MMF, the MMF generated by the machine and all, then it is quite simple to execute the transformations. So here, if you have a look at this, the three-phase to two-phase transformation is what we call as Clarke transformation, where the three-phase system, which is having A, B, C, for example, is converted into alpha and beta. So that is called three-phase to two-phase transformation. And this alpha to beta transformation, that is what named as path transformation, is converting that stationary frame into rotating frame. So alpha beta is the stationary frame which is obtained by performing the Clarke transformation and converting the three-phase into two-phase. and you are having alpha beta frame that is stationary, that two phase frame is stationary, and you are converting that into rotating frame, that is called DQ frame. And go to the other side, which is explaining the inverse Park and inverse Clarke transformation, right? Hope this is clear and it is giving you an idea. And again, have a look at the bottom, the blue colored line and blue colored indications. From three phase to two phase, it is AC system, right? And when we are going to stationary to rotating, that is here DC actually, right? The D and Q are nothing but direct axis and quadrature axis currents, okay? They are direct axis and quadrature axis current. So have a look at this fundamental things which you require for the conversion of ABC to alpha beta, three phase to two phase transformation. IA, IB, IC are the stator currents of three phase induction motor, and NS is the number of stator winding turns per phase. FA, FB, FC are nothing but the MMF generated per phase respectively. FA is MMF of phase A, FB is MMF of phase B, and FC is MMF of phase C, which is generated by the respective currents IA, IB and IC, right? So the current flowing through each stator winding will generate an MMF. That is what I said. IA will generate an MMF of FA, IB will generate an MMF of FB, and IC will generate an MMF of FC. Now these MMF, the resultant MMF, will produce a rotating magnetic. These are the fundamental things which you already very much aware of, right? All these things are already known to you, and this rotating MMF can be represented by a space phasor. Have a look at this diagram. I couldn't find a diagram with a better clarity, bear with me for that. Have a look at the three-phase conventional three-phase system diagram. All the three phases are displaced by 120 degree between each other. Again, this is a very fundamental thing which you all know. Current flowing through phase A winding is IA, and for B and C winding respectively IB and IC. Similarly, the MMF produced by A, B and C windings are, or A, B and C phase windings are FA, FB and FC respectively. They are having 120 degree displacement between each other. Again, the fundamental equations of the current. Current IA is Im cos omega t, current IB is Im cos omega t minus 120 degree, and IC is Im cos omega t minus 240 degree, and this is written here in radians. Now we are going to see how we can perform the transformation from three phase to two phase. So here we are converting the most important thing, or the important constraint to be taken into account is that when you are making the transformation, the power in three phase system and two phase system should remain same. It shouldn't change. So the power must be invariant during the transformation when you are performing the transformation from three phase to two phase, right? And here we are moving to alpha beta from three phase system, that is ABC, we are moving to alpha beta. Alpha beta stationary balanced two phase windings are displaced by 90 degree. What we were seeing in the previous case, here the phase windings A, B and C are displaced by 120 degree. Here the windings alpha and beta are displaced by 90 degree. And the coils alpha and beta are so placed that the MMF produced due to the coils A, B and C are same as to that of the MMF produced by the coils alpha and beta. That's we explained in another way around that the MMF produced by the coils alpha and beta should be same as to that of the MMF which is produced by the phase windings A, B and C. So now let us see how this transformation can be done. Before that we will see the equivalent current equations for the alpha and beta frame, right? So here the two diagrams are taken into account for consideration, and this is giving the phase current for I alpha and I beta. I alpha is Im cos omega t with respect to the diagram which we are seeing here, this two phase winding diagram which we see here. I alpha is Im cos omega t and I beta is Im cos omega t minus 90. That is Im sin omega t. So now we have the equations for three-phase winding IA, IB and IC. Similarly, we have the current equations for phase current equations for I alpha and I beta. Now just have a look at the point which I mentioned. This current results summum of constant magnitude of I into N. The very again, as I mentioned at the beginning of the video, that if you are good enough with the fundamental equations and concepts of three-phase system, then it is quite easy to understand the transformation. Right? Have a look at this point. These currents are results MMF of constant magnitude I, and I into M is what? Current into the number of turns, right? So here the MMF in both A, B, C and alpha beta should be same, because that is what we already discussed, right? Since the current is going to be same, then the MMF must be same. The MMF produced with the equivalent MMF, right? That is what we what I just explained now. The MMF produced by the AB three-phase system or the MMF produced by the two-phase system should be same as to that of the MMF which is produced by the three-phase system. Then only your transformation will become effective. And it can be achieved by three different techniques. That is by keeping the number of turns per phase constant and varying only the stator current, or by varying the stator and or by keeping the stator current constant and varying the number of turns per phase, or the third technique is varying both of them. So in the first technique, keeping the number of turns per phase constant and varying the stator current. So in the first technique, that is by keeping the number of turns per phase constant and varying the stator current, the equation is what we have already seen. I alpha is equal to, so in order to see this again, we should go back to this diagram. So you need to compare these two diagrams in order to write these equations. So I alpha is Ia cos 0 plus Ib cos 120 plus Ic cos 240. Now what we are doing, we are comparing we are trying to make the equivalent phase current for the two-phase system from the three-phase system. That is what we are doing here. So in order to do that, to see the fundamental equation from the based on the basic equations and the diagram which we have already seen, we can easily write this equation, right? For alpha and beta, you can write this equation. I alpha is equal to Ia cos 0 plus Ib cos 120 plus Ic cos 240 degree. So the values for cos 120 and cos 240 are minus 1 by 2. Therefore, you can rewrite the equation as I alpha is equal to Ia minus 1 by 2 I beta minus 1 by 2. Ia minus 1 by 2 Ib minus 1 by 2 Ic. But so here the entire stuff which is shown here, all the equations are showing how the equation is rewritten in order to get the final equation. Therefore, finally we are getting I alpha is equal to, by substituting, because in the balanced system Ia plus Ib plus Ib Ic is equal to 0. Therefore, I alpha is equal to 3 by 2 Ia. Similarly, we will get Ib also, I beta also. So I beta equation is now, see, again we have to go back and compare I beta with the three-phase system. So I beta is equal to Ia sin 0 plus Ib sin 120 plus Ic sin 240. In the previous case, if you see, I alpha is having cos and I beta is having here sin. But this will give you the final equation. I beta is equal to 3 by 2 into Ib minus Ic, because sin 0 will cancel Ia tan, right? When you are going to write it in the matrix form, I hope you remember what I just explained at the very beginning here. I'll just go back to it once again. New variable is equal to transformation matrix into old variables. Now we have the equivalent values for I alpha and I beta based on ABC, and we are going to put it in the matrix form. So I alpha, I beta is equal to, this gives the equation, right? That is completely derived from what we have seen here. This one. 1 minus 1 by 2 minus 1 by 2 ABC and the second equation is 0, 3 by 2 and minus 3 by 2. That is what being written here, right? So this is the equivalent matrix, or we can call this as a Clarke transformation equation. It's not over here, we will have a look at it further. So the second method is to keep the stator current constant and varying the number of turns per phase. That can be done. See the two equations, the fundamental equation again. Effective number of per phase turns of two phase winding equal to 3 by 2 times of number of windings of three phase winding. So if you want to convert this three phase winding into two phase winding, it's a very basic equation. You have to multiply the factor of 3 by 2 with the number of turns of per phase turns of three phase winding, so that you can divide it into 2. Now we are concerned the factor of varying both the number of turns and the number of turns per phase and the stator current. Now look at this equation. So number of turns per phase of two phase system is equal to square root of 3 by 2 into number of turns per phase of three phase system. Similarly, current in the three phase system is two phase system is equal to square root of 3 by 2 into current in the three phase system. So resolving that, we will get I alpha into root 3 by 2 in ns is equal to ns is what? Number of turns per phase. The equivalent equation. The equation simply we are substituting the values of two phase system and three phase system, so that we are getting I alpha into root 3 by 2 ns is equal to ns into Ia minus 1 by 2 Ib and minus 1 by 2 Ic. By rewriting the equation, what we will get? We can cancel ns from both the left hand side and the right hand side. So obviously we will get the final equation of I alpha is equal to what? Square root of 2 by 3 Ia minus 1 by 2 Ib plus minus 1 by 2 Ic. So the additional term which comes here is square root of 2 by 3. Similarly, the same case for I beta is equal to square root of 2 by 3 into 0 plus 3 by 2 Ib minus 3 by 2 Ic. So this is the transformation matrix for the Clarke transformation. I alpha and I beta is equal to, we just derived, we just put that in the matrix form. So just in order to make it as a square matrix, what we are doing is we are adding a third current component, but which should not make or should not affect the system. So here we are adding a third current component in terms of ABC, which does not produce any other MMF, or it can be called a zero sequence current, right? So a zero sequence current component is added into the matrix to make it as a square matrix, which is not affecting the overall system performance by producing any resultant MMF, right? So the final equation is written here. If you have a look at it, it is I alpha, I beta and I0 is the zero sequence current component in order to make the equation, the matrix, transformation matrix, a square one. The transformation which we have seen here is what we call as Clarke transformation. Right? Have a look at these diagrams. The three-phase reference frame is converted into two-phase reference frame, where we have A, B, C currents. They are converted into two-phase currents, alpha and beta. So when we are talking about inverse Clarke transformation, it's just the inverse of what we have done for the alpha, beta and 0. Right? The inverse matrix of the same in order to get your inverse Clarke transformation. Just to have a look at this, I am not going to explain much about this because this is just the inverse matrix of the Clarke transformation. Alright, I will move on to the next slide. Now we are going to discuss about the path transformation. Path transformation is nothing but converting that reference frame into a rotating frame. So what we have seen, as I mentioned before, ABC frame is converted into alpha beta frame where the three-phase system is converted into two-phase. Again, in alpha beta, the stationary two-phase or stationary frame is converted into a rotating frame. That is what being done here. So have a look at this phasor. This is very important. The stator axis alpha and beta and the rotating axis D and Q. It has an angle displacement of theta, right? It has an angle displacement of theta here. This is a resultant current. We are not getting into it because we will see how we are going to write the equivalent equations for D and Q from alpha and beta. Okay? This diagram is showing what is being done. Three-phase reference frame is converted, ABC is converted into alpha and beta, that is being converted into rotating reference. That is what I said. Here this is a stationary frame. It is converting the three-phase system into two-phase system. That two-phase stationary frame is converted into two-phase rotating frame. So here we have the direct current and the quadrature current. Right? Direct axis current and the quadrature axis current. This is giving the general introduction about how we are going to, the basic concepts to be taken into account. Now look at the third point, F alpha and F beta are the MMF space vector for alpha and beta winding. Similarly, F D and F Q are the MMF for the DQ winding. So at any time T, theta is equal to omega r into T. Omega r is nothing but the angular velocity with respect to time. So it varies with respect to the angular velocity will vary with respect to time. I mean the displacement angle will vary with respect to time and the angular velocity. So have a look at these equations. The MMF produced by the direct axis is the components, has the components of alpha and beta, alpha cos theta and beta sin theta, and the other way when you are writing it, n into I direct axis is equal to n into I alpha cos theta plus n into I beta sin theta. The same equation, first and second equation are same. Here this is MMF, that is rewritten as n into I, number of turns into the current in the direct axis. So these notations you know why we are writing cos theta and sin theta, so I am not going into it. Therefore ID, by cancelling out these things, you will get ID is equal to I alpha cos theta plus I beta sin theta. It's clear. So in the same way you can write the quadrature axis current. Quadrature axis current is taken into account here. See, minus I alpha sin theta plus I beta cos theta. So when you are going to write them in the matrix form, this will give you the matrix here. ID IQ is equal to, see, matrix of cos theta. So this is simply converted into the matrix form. Again here what we are doing, we are adding a zero sequence current in order to make the matrix square. So ID IQ I0 and it is simply written. Right? It's clear? So this is what we call as path transformation. Once you are able to understand the Clarke transformation, it's very easy to realize and perform the path transformation from the alpha beta frame. This is giving the inverse path transformation. So we have seen the ABC to alpha beta conversion and from alpha beta to DQ conversion also. We have written here. If you have a look at the first set matrix ID IQ with respect to I alpha I beta, we already have an equation for I alpha beta with respect to I ABC, that is substituted here, and by solving this you are getting the equation for ID IQ and I0 as the components of IA, IB and IC, right? So what we did here, we initially did the transformation of the three-phase system, three-phase stationary reference frame into two-phase stationary reference frame, that is from ABC to alpha beta transformation. Then from there further we did the conversion of alpha beta, that is stationary reference frame, into the rotating reference frame, that is called DQ. So by performing these two, we got two transformation technique. Actually, that ABC to DQ transformation is done the conversion is called Clarke transformation, and alpha beta to DQ transformation is called path transformation. Now they are both put together in such a way to get DQ in terms of ABC. That is the final equation you are seeing here. So this is all about the transformation techniques which are used to simplify the three-phase reference frame into two-phase reference frame for the implementation of better control of induction motor drive. Thank you for watching.